Hello everyone, welcome to Biot-Savart Law and its applications, the third application, to find the magnetic field due to a straight conductor. Now let's find the small magnetic field, which is mu naught by 4 pi IDL sine theta by r square. Now this is a bit different from the previous two applications because first of all they were for circular coil, and for here there are some variables. So here let's take a point P in which we have to find the magnetic field, and we have took a current element at point C at a length L from this O, let's say, which is the mid of the whole conductor, midpoint of the whole conductor. Now let's say you had not taken the current element there, instead you have taken it over here. What would happen is, well, the radius would increase and also the angle would change. And here in fact you can choose the current element to be anywhere, and the radius would keep changing and the angle would also keep changing. What that means is this sine theta is a variable, this radius is also a variable, and due to this length, its small length dl, because we just differentiate the length, will also be variable. That means there are too many variables, and in which it will be very difficult to compute, nearly impossible. So we put these variables in terms of some constant. So here, if you had noticed while I was doing this, on which the current element's position was changing, that this length A from the mean position will always be constant. From the mid position to this point, this horizontal distance A will always be constant. Only the radius would keep on changing. So from the help of this triangle, we can put radius in terms of A and also this length in terms of A as well. So for now, let's keep it at point C and find radius in terms of A. So radius, well, let's take the help of alpha, because here this angle theta, we also need to turn it into, well, alpha first, right? So here let's just find it for angle theta. Angle theta in terms of alpha. So here theta will be equals to, if this is 90 degrees, then the remaining angle will be 90 degrees. So these two add up to 90 degrees. That means that theta is equals to 90 minus alpha. 90 minus alpha, meaning sine theta will be sine 90 minus alpha, which is just cos alpha. Now for the radius part, here this A in terms of alpha is, well, the base by the hypotenuse, which is cos alpha. So cos alpha is equals to the base A by its hypotenuse r. So r is equals to A is equals to r cos alpha, and from here r is equal to A sec alpha, because, well, we can simply multiply both sides with sec alpha, these two would cancel, and here we have found the relation between r and A. And again, let's find it for length L. So L is equals to, now this time it is the perpendicular, so it will be, well, sine alpha, which is L by r. We need to find in terms of A. So in fact it will be perpendicular by base, which is tan alpha, which is L by A, perpendicular by base, and A tan alpha is equals to L, right? And, well, we have already found the relation between L and A tan alpha. So I'll put L here for simplicity, and I'll differentiate both sides, which will be A, which is a constant, and this tan alpha, well, this angle alpha will also be variable, of course. So it will be sec square alpha d alpha. Now let's just put all of this in this equation right here. So I'll highlight the one. So this, and this. So dB will be equals to mu naught by 4 pi I a6 square alpha d alpha. Sin theta is cos alpha, and radius is a6 sec alpha, so this is squared. And here this square cancels, this whole sec square alpha cancels, leaving us with dB is equals to mu naught I cos alpha d alpha by 4 pi a. Now here we need to integrate both sides, so I'll rewrite it again with integration symbol. Mu naught by 4 pi I cos alpha by a d alpha. Now what is the integration symbol? Now for this one we need to talk in terms of angle, because here instead of the dl, which was the length element, which also correlated to the current element, but here we're talking in terms of alpha, and here the alpha changes from, well, to its max upper length to its max lower length, sorry, the max upper position to the lower upper position of this straight conductor. So let's say this is alpha 1 and this is alpha 2. Now we need to take the clockwise and anti-clockwise in consideration. So here this is going anti-clockwise, so it's taken as positive, and this alpha 2 is going, well, clockwise, so it is taken as negative. So it will go from negative alpha 2 to alpha 1. So this is magnetic field. Let's take all of the constants outside. Mu naught I 4 pi a, and the cos alpha's integration is sine alpha. So sine alpha 1 to minus alpha 2. Now if you plug in here, it will be sine alpha 1 minus sine of minus alpha 2, and of course we know that sine minus, well, anything, let's just say beta, will equals to minus sine beta. So simply mu naught I by 4 pi a, it will be sine alpha 1 minus sine, well, alpha 2, which will be plus sine alpha 2. This is a required expression, but for numericals we need to go further. We need to find out when it is of, this AB is of infinite length. Now don't be confused by the use of word infinite, because here infinite doesn't actually mean infinite, because that really doesn't exist in real life. What this means, it is very very long, such that magnetic field, because it is very weak, would act as if it is infinite. So that means we need to find alpha 1 and alpha 2 simply. So here alpha 1, if this is very long, this will be, well, it will go like this, and almost it will be alpha 2 will almost be pi by 2, and here we take it as pi by 2, and similarly alpha 2 will also be pi by 2. So if we plug pi by 2 in these equations, well, both of them will be 1. 1 plus 1 is 2, of course. 2, and this cancels, giving us that B is equals to mu naught I by 2 pi a. This is the required expression, and here there are no n number of terms, because of course this is a straight conductor. Thank you, and if you learned something new, please like and subscribe.